Good morning. Let's discuss today Zener diode and its characteristics, and as an application we will discuss the voltage stabilization using Zener diode. Okay, so what is Zener diode? So Zener diode is a special type of PN junction diode that is used in electronic circuits. So it works on the principle of Zener breakdown, which is shown in this graph. The x-axis is voltage and y-axis is current. So Zener breakdown voltage is Vz, which is shown here. That is, in a Zener diode, the doping is very high. That is, it's heavily doped, so that the depletion layer is very narrow, or the PN junction is very narrow in this Zener diode. Hence, when a reverse voltage is applied to the diode, there will be large electric field in the junction region, which tears out electrons from the atoms in the region. So how it is working, how a Zener is conducting. So the Zener diode is always reverse biased, always connected as in reverse biased mode. So whenever a reverse voltage is applied to this Zener diode, there will be large electric field in the PN junction region, which is very narrow in the case of Zener diode because of its heavy doping, and which causes the pulling out of electrons from the atoms in that region. So thus a large current will flow in the reverse biased condition. This is called Zener breakdown. So what happens is, when we are applying a reverse voltage, so whenever we are applying a reverse voltage, so at a particular voltage, that is at the Vz, electrons are pulled out from the atoms, and then it starts current flowing, a large current flow in the circuit, which is in the reverse direction. So reverse voltage, so this is working in the reverse voltage, and so reverse current is obtained. So this voltage is known as breakdown voltage, at which the current is shooting out in the reverse direction. So this voltage is known as breakdown voltage, and this region is known as Zener breakdown region, where the current increases sharply. Okay, in such case, the voltage across the diode will be constant irrespective of the current. So here you can see that the current is increasing in the reverse direction, but the voltage is constant, because whenever the breakdown voltage is reached, then the current is increasing, but the voltage remains constant. Okay, so a Zener diode is always operated in the reverse biased condition. So this is always operated in the reverse biased condition. So the Zener diode will be working only if it is reverse biased. So this is about a Zener diode. The forward characteristics of a Zener diode is similar to that of an ordinary diode, but the reverse characteristics are different. At low reverse voltage, what happens? The reverse current will be very small, but at a particular value of reverse voltage, the diode undergoes Zener breakdown and the current rises sharply, which is quite clear from this figure itself. Until the breakdown voltage, the current is nearly zero, and at the breakdown it increases sharply. Okay, the voltage across the diode remains still constant irrespective of the current. So this is the characteristics of a Zener diode. Okay. So as the curves reveals, two things happen when Vz is reached. The diode current increases rapidly, and the second thing is the reverse voltage Vz across the diode remains always constant. In other words, the Zener diode operated in this region will have a relatively constant voltage across it, regardless of the value of the current through the device. This permits the Zener diode to be utilized as a voltage regulator. Okay, so this is the special characteristics of Zener diode, that is, until the breakdown voltage the current is 0, and at the breakdown voltage the current increases sharply in the reverse direction, since it is reverse biased. But the voltage remains constant, though the current is increasing. So this particular character, that is, voltage remains constant regardless of the values of the current, is utilized as the Zener diode as voltage stabilizer. So Zener diode can be used as voltage regulator because of this particular character, that is, voltage remains constant irrespective of the increase of the current. So this is the characteristics curve of Zener diode, and the symbol of the Zener diode I can show this here, and we can discuss the Zener diode as voltage regulator. Here I can show you Zener. Yeah, Zener diode as voltage. So yeah, this is the symbol of a Zener diode. Okay. Yeah, Zener diode. So a properly doped crystal diode which has a sharp breakdown voltage is known as Zener diode, which we have already discussed. And Zener diode is like an ordinary diode, except that is properly doped so as to have sharp breakdown voltage. This point we also discussed. A Zener diode is always reverse connected, that is, it is always reverse biased. A Zener diode has sharp breakdown voltage called Zener breakdown voltage. So these are the characteristics. When forward biased, its characteristics are just those of ordinary diode. The Zener diode is not immediately burned just because it has entered the breakdown region. As long as the external circuit connected to the diode limits the diode current to less than burned out value, the diode will not burn. Okay, so these are the when it is forward biased, it behaves like an ordinary diode, but when it is reverse biased, this behavior is different. That is just as we discussed before. So this is the symbol of the Zener diode, an arrowhead and with a Z-shaped bar at the end. This is the symbol of a Zener diode. So the particular characteristics of Zener diode, that is, the voltage remains constant regardless of the increase of the current in the circuit, can be utilized for using Zener diode as a voltage stabilizer. So let's discuss Zener as a voltage stabilizer here. So for using Zener diode as voltage stabilizer, the Zener diode can be included in the circuit as shown in figure. So here is the input voltage, and the Zener diode is reverse biased with this input voltage. Here the positive terminal is connected to the negative bar head, negative bar, and positive to the negative. So it is reverse biased, and this is the input resistance and this is the load resistance. This is the connection diagram. So what is voltage stabilizer means? So there may have voltage sources which show variations in this in its voltage outputs. So this type of circuit arrangements or the particular characteristics of Zener diode can be utilized in order to stabilize this variation of this voltage sources, and we can produce a constant voltage at the output. So the fluctuations in the output voltage can be maintained constant by the Zener diode, and such a circuit is known as a stabilization circuit and or stabilizer. Okay, so how this is working? So Zener diode works on the principle of Zener breakdown. So we have seen it just before. It is always used in the reverse biased condition that we know. When the Zener diode is in the breakdown region, the voltage across it will remain constant regardless of the current through it. So this particular property is utilized for stabilizing the fluctuations in the voltage. Okay. So in this circuit, the input voltage from the battery is given to the Zener diode in series with a resistor, which we have shown here. The load resistance is connected in parallel with the Zener. The Zener is operated in the breakdown region. When the input voltage increases, there is a large resistance in the there is a large increase in the Zener current. So the input voltage increases means there is a large increases in the Zener current after the breakdown. This increased current also flows through the series resistor. This resistor and causes more voltage drop across it. So the current increases as the input voltage increases, but this increase in voltage causes increase in current which is dropped across this series resistor. And what does this mean? This maintains a constant output voltage across the output voltage. So this output is unaffected. Whatever be the output, it will remain so. So the extra current or the extra voltage will drop out across this resistor. Okay, due to this Zener diode, because the Zener current is increasing and which will drop out across this resistance. Okay, this causes a decrease in voltage across the series resistor, so that the output voltage is not affected. This output voltage is constant irrespective of the change in the input voltage. And if the series resistance R, the total current is I, then again one more point. Yes, we have discussed that point. Now suppose that input voltage is constant but load resistance RL decreases. So first we discussed the increase of input voltage and we discussed that case. Now suppose that this is constant but the load resistance is changing, that is decreasing. This will cause an increase in the load current. The extra current cannot come from the source because drop in R will not change as the Zener is within its regulating range. The additional load current will come from a decrease in Zener current IZ. Consequently, the output voltage stays at constant value. So this is again stabilizes the output because even though the load resistance decreases, what happens? This will cause an increase in the load current. Okay, the extra current cannot come from the source because drop in R, and hence the source current I will not change, because the Zener is always in the regulating region, because in the breakdown region, so it regulates the current and voltage. It always regulates the voltage, so no change will be affected at the output voltage. This is how the stabilization process occurring. Okay. And voltage drop across R can be represented as EI minus E0. So the difference in input voltage and output. So this is the voltage drop across R, the series resistance R. So this minus this. So whatever is flowing through this load resistance and the input voltage EI, the difference will be that dropped across the R. So we can give voltage drop across R as EI minus E0. Then current through R as IZ plus IL, that is through Zener and load resistance. Okay. Therefore, applying Ohm's law, we can get from this is V and this is I. So V is equal to IR. Therefore, R is equal to V by I, that is EI minus E0 by IZ plus I. Okay, this is so this must be the value of R, that is the resistance that must be included in the stabilization circuit here in order to stabilizes the voltage. Okay, so this is how a Zener diode stabilizes the voltage, fluctuating voltage source. Okay, so that's all about Zener diode as voltage stabilizer. Thank you.